Hey, welcome to project number 3 in this packet, which should be maybe a little bit more familiar to us because we just finished, way back, what seems ages ago, we did a chapter on exponential and logarithmic functions. This right here is geometric sequences, and they're sequences that grow by continually multiplying by the same number. That's exponential growth. How many earths of rice? Right, 38 earths. This is the same idea on how these work. The interesting thing is now that base number that we multiply by repeatedly actually could be positive or negative. In exponential functions, it can't be. We explored that a little bit in class. But now, because it's just a sequence of numbers, there's no reason why we can't repeatedly multiply by negative. And what that does is has an oscillating effect. It goes from positive to negative, positive to negative. It's kind of a cool way of looking at it. But remember, we're multiplying by the same amount each time. And that common ratio, we call it, not common difference, that was D. Now we're multiplying by the same number, and that common ratio is called R. And if you think about it, how many R's do I multiply a first term by to get the second term? A single R. How many R's do I multiply a first term by to get to a third term? 2 R's. To get to the 10th term, how many R's do I multiply by? 9, right? So there's always going to be one less. Now, how do we show repeated multiplication? That is with exponents. So we end up with this is arithmetic. Now we're talking about geometric. And an nth term is going to be my first term multiplied repeatedly by some common ratio R. Well, how many R's? If I'm starting with the first one and I want to jump to whichever one, then I multiply it by that many minus 1. Okay? The 10th one is going to be my first one times 9 more of those R's. Now these numbers go just crazy, astronomically large very quickly. This one here, number 10B, was over 2.6 million as just my 20th term. But that's, again, no surprise to us. We spend a lot of time with exponential growth. We know how quickly numbers can grow. What if you want the numbers to get smaller? Do you still multiply? Always. You always multiply. But if you want a number to get smaller as you repeatedly multiply, that means that you're going to have to multiply by another number between 0 and 1, a fraction less than 1, or a decimal. Okay? So that's how these things work. Moving forward and backwards, yes. If you multiply going forward, going backwards, you can divide by that and work all the way down to whatever number you want. And that works out pretty nicely. I'm trying to think if there's anything else on this. Yeah, not really. Though I do want to make a mention of number 13. I did have a typo on number 13. So if you're working through that and you said, well, that doesn't make sense, because the first 5 terms should be terms 1, 2, 3, 4, and 5. And this right here, this sequence begins as the 9th term of 15,000 with a common ratio of 1.08. It's a great example of money that you put in a bank account that grows at an 8% interest. You get additional 8% along with your 100%. That's a 108% increase as each year goes by. At the 9th year, if you had 15,000, how much did you have at year 1? Well, then in that case, you would take the 15,000 and divide by 1.80. If you divide by that once, you get here. So this is your 8th term, 7th term, 6th term, 5th term. I stopped there. I shouldn't have. I should have gone again to 4th, 3rd, 2nd, and 1st. I believe it's around 8,100. So again, my apologies for this. To jump to find the 50th term, you would then take your first term that is incorrect here. It should be around 8,100. The first term times 1.08 raised to the 50 minus 1. Or could we have simply taken this number, 15,000, and multiplied by 1.08 raised to the 50, because that's what I want, minus 9, because that's the term number I started with. That would have worked as well. In any case, this is not the correct answer. The correct answer would be something different other than that, you can type this into Desmos and figure out what that would be. All right, so I think that is it for Project 3. I'll see you at Project 4.